Road testing makes autonomous vehicles safe. Truth or myth? This one's a myth. Road testing is not enough to make them safe. Let's explain why. Well, let's start with the basic robot driver test. Let's pretend this is an ordinary human driver who has to go through the testing process to get their license. They do a vision test and they do some other stuff. And then they do a written test to make sure they know about the traffic laws. And then there's a road test, testing whether they can obey traffic laws, whether they can negotiate effectively with human drivers, and whether they can resolve some example potentially ambiguous situations. All right, let's say that a robot driver does all those things. They pass a written knowledge test of some sort. They pass a road test where they drive around for a mile or so, and the examiner says, yeah, okay, this thing knows how to drive. Does that get you everything you need for safety? Well, no. There's another much more important requirement beyond all these that is levied upon human drivers, and the question is how we do that with robot drivers. And that requirement is you have to be a 16-year-old human in most places to qualify for a driver's license. And the reason we do that is it's a proxy for maturity of judgment. Now, we can have all sorts of snarky remarks about how immature 16-year-olds are, but the fact is they've had 16 years to figure out how the world works. They can do a really good job of walking into an unstructured situation and figure out what happens next, having never seen the situation before. Beyond that, there are some maturity of judgment factors that come into play. Some of it's experience, some of it's growing up. But the baseline of a 16-year-old person to be able to predict what happens next in an unstructured situation is amazing. And this is a big thing that machine learning-based robot drivers struggle with. So we need a proxy for maturity of judgment and experience with how the world works, and it's not clear how to get that on just testing. And this is why you do not see safety-critical systems generally tested and tested and tested to prove they're safe, because it just takes too much testing. Instead, what you see is engineering rigor used as a proxy for maturity of judgment. So rather than seeing, well, can they reason well, we say, you know what, we've done a lot of engineering to make sure we've designed in all the behaviors that we need, and that's why we know they're safe. So a robot driving test doesn't prove that happen. You need something else. Now, if you don't want to go with engineering rigor, if you really, really want to go testing, what you have to do is a whole lot of testing. The reason is you need to make sure a robot driver can deal with the vast majority of the strange, unusual, rare stuff that's going to happen on the roads that's still relevant to safety. If you're looking at 100 million miles per fatality as a ballpark number, you're going to need 3 to 10 times that to get statistical significance. So we're talking a billion miles of testing, more or less. How much is that? Well, that's 50 times on every road in the world. That's a lot of miles, right? It's a huge amount of driving. And by the way, you might have to start over after every software update if you can't prove that the update did not disrupt previously learned behaviors, which in fact is a problem for machine learning. If you teach it new things, sometimes it forgets old things. So this is really just a huge amount of brute force testing. It's just not practical. The challenge is covering everything. Have you covered all the possible unknowns? Have you run out of unknowns to the point that everything's pretty much nailed down, at least in the environment you intend to operate in? Here are some examples of unknowns that range from the pretty common to the crazy, but it's to give you an idea of the span of things that you might need to be able to deal with. One of them is that driving into water is tough, whether you're a human driver or a robot driver. Here's a picture of a pickup truck that drove into a puddle a little deeper than they thought it was going to be. You have to know to not drive into water unless you're really, really sure about what the depth is going to be. There's another one. Every once in a while you get a very, very complicated road arrangement. This one's called the magic roundabout. This is a pretty well-known thing, so it shouldn't be a surprise. But if you're going to drive on that road, you'd better know how to deal with this. Then you have the weird road actors. Here's a person in a chicken suit, but there are people in costumes on roads all the time, not just during Halloween, but especially during Halloween. You need to realize that this is a person and should be treated as such, and you also need to realize that the behavior of this thing is going to be more like a person than a real chicken. Then there's the truly bizarre stuff. Now you may say this is crazy, airplanes aren't on roads. Well, beyond there being a picture, I've personally experienced this. When you go on some military air bases, there are stop signs and you're not stopping for cars, you're stopping for aircraft going from the flight line out to the runway. So this is a thing. If you want to really drive everywhere, you have to deal with some really unusual things that you're sharing the road with. And then there's the things that don't seem that odd but are actually surprisingly subtle. Here's a person and a bicycle. Now, is this person riding the bicycle or is this person standing next to the bicycle and holding it? Most people would say probably standing next to the bicycle and holding it because the feet are flat and there's one hand on the handlebars. Where's all the details in color? Well, maybe this person's backlit at sunset and that's basically all you're seeing as a shadow. People are really good at figuring out this kind of stuff. The expected speed of a person riding a bicycle is much, much different than a person pushing a bicycle than a person standing still, and those predictions are going to matter. So these are the kind of things you need to be able to deal with, and it's just a small sample. If you want to be able to drive safely in the world, you need to know not only what the things are, but what's going to happen next. And good prediction is based on a world model. You have to have good classification, and you have to have prediction based on that classification. Here's an example. Here's a person. How do I know it's a person? Well, it's something, looks like coat, looks like shoes, looks like feet on, and maybe some arms holding an umbrella. So I'm going to say it's a person, even though you can't really see that it's a person, but it sure looks like a person to me. Okay, so here's a person, and what happens next? Well, their feet are together, so it looks like they're going to stay still. And so I'm not predicting it on they're motionless, so they'll stay motionless. I'm predicting it on posture, which is what human drivers tend to do. And what happens next, though? What are the chances this person decides to cross? Because they're in a marked crosswalk, so you'd better yield. Well, right now, hard to say. Probably not going to move, but we need to keep an eye on this. But the reality is there are multiple possibilities. There is a chance this person will, for no reason, run out in front of me. Or maybe they run in front of me for a reason. Safety is limited by the heavy tail scenarios. These are things that are rare but important. The probabilities of what happens next turn out to be context dependent. So looking at this, there's fairly low risk that this person will run out in the street. But what if there's a bus pulling up across the street and then the person sort of leans forward and looks like they're in a hurry? Even if they have a red light and they're not supposed to cross, they may well run across the street to catch that bus because that's their bus and it's another half hour before the next bus comes. Those kind of subtle contexts are the kind of things that human drivers are pretty good at, and machine learning will be bad at unless it's been taught about these specific scenarios. But this is a high-risk scenario. This is a scenario where you can reasonably expect a pedestrian in a marked crosswalk, mind you, will run out in front of you even though they have the don't walk sign because they're worried about missing the bus. This is the thing that happens. And if you want acceptable safety, these are the kind of things you're eventually going to have to deal with to get there. Safety lives in the rare cases. Rare cases with unusual context are ultimately going to determine whether this technology is as safe as it needs to be or more dangerous than a human driver, even if not crazy dangerous. More generally, the concern is that there will be a lot of surprises that the machine learning has to learn, and there may be lots of surprises as not just a long tail, but a heavy tail. So let me explain the difference. In a typical distribution, people love to assume random independent arrival events, so it's an exponential curve. And the idea is you test for a while, and eventually you test so much you've seen almost everything. You have almost all the area under the curve. And the things you've not seen in testing are so infrequent that you can say, we'll roll the dice. We'll still be 10 times, 100 times safer than a human driver. And so it'll be unfortunate, but when we see them, we'll fix them, and we can live with that kind of outcome. And if this were really the distribution, maybe that would be okay. But there's good reason to believe that's not the distribution. The distribution seems more likely to be a heavy tail, a power law, 80-20 rule. And the idea is there are fewer things that are common and many more things that are very rare. So it's not how often a thing happens that's rare, it's how many rare things there are to happen to you. And the difference is really important. And on the next slide, I'll do a different example to really bring that home. But here, the problem with this, if you have a power law arrival rate of the types of surprises as opposed to how many surprises arrive, that takes all the difference between those two curves and throws it out to the long tail. That makes it heavy tail, which means you have a ton of things you have to deal with, and they're all individually rare. So let me give you a concrete example to explain that somewhat theoretical graph. Let's say that you're going to do 1 billion miles of validation testing. Let's say it's 1 million miles between unsafe surprises. So you have 100 surprises. So you've done all this work and you aren't quite where you need to be. So you're going to test a bunch to get the last surprises, and there are going to be 100 surprises, each one at 100 million miles per surprise. So these are really rare things. You're going to say, okay, fine, I'll do 1 billion miles. I'll see each one of these on average 10 times. For sure, I'll notice a few of the times, if not all 10, and I'll fix them. Okay, great. Then you're notionally perfect. This is a hypothetical example. I just picked some numbers. Let me contrast this with a different situation, because example 1 is probably not how it's going to really work. Example 2 is based on the notion that there's a lot of really weird things out on the road. How often do you see a house that looks like this mounted on top of a car? I've never seen one in person, but there's a picture, so it exists. Okay, let's say there's a ton of weird things, and nobody has seen them all. That looks more like this. It's a heavy tail distribution. Instead of 100 surprises, there's 100,000 surprises. And again, I'm just picking a number to illustrate. Well, for it to happen 1 per million miles, that means it's 100 billion miles per surprise. So there's a huge number of things, each of which is extremely rare. And you can say, well, 100 billion miles, why should we worry about it? Well, you should worry about it because one of them is happening every million miles. The problem is, if you fix each one as it happens, it doesn't do you any good. Because after 1 billion miles, you've only fixed 1% of the problems. 99% of them are still there. And the things you fixed, you probably won't see for another 100 billion miles. So the drive around and fix stuff stops working when you get out into the heavy tail. And that's the concern. The concern is that this technology, based on machine learning, only learns when you have examples to feed it. And the limit to safety is going to be how often and how many different types of weird things there are, where you just sort of hit a wall that you're just not able to predict the next surprise that's going to happen because they're so rare, but there's so many you can't ignore them, but you also can't predict them. That's the concern. So how does this fit with safety engineering? Well, here's how safety engineering works, and we'll get to why this is a problem for safety engineering. The way safety engineering works is you identify the hazards. Here's all the things that can go wrong. You determine the risk from hazards. Some things that can go wrong kind of don't matter, and some things that can go wrong are a big deal. And you apply engineering rigor in proportion to the risk presented. And the really risky things, you apply a lot of engineering rigor to make sure you mitigate the risk. And the things that aren't risky, you don't worry about, or you do minimal amount of mitigation because they don't matter. And you repeat until you have an acceptable remaining risk. So you go out and you find all the hazards, and you decide which ones need mitigation, you mitigate them, and when that process settles and you stop finding new hazards, you're done. The open challenge is, if you have a heavy tail distribution, maybe you never stop finding hazards, and maybe you have a steady stream of high-risk hazards. We don't know how that's going to turn out. We hope that over time, the high-risk hazards will dwindle to the point that the remaining risk is acceptable after mitigation. But we're still in that process. That's why years later, these cars are still running around finding new things to fix. We don't know how long that's going to take. And until that settles down, it's going to be difficult and probably too risky to go to really big scale. A different way to go is to apply really good engineering practices to get the machine learning safe without all this testing. But we don't know how to do that. We're still working on that. And finally, we have these questions about how much and what type of remaining risk is acceptable. That gets into the discussion of, well, how safe is safe enough? And so if you have an answer for how safe is safe enough, you then have to map that into the safety engineering to know how far into the heavy tail you need to get to really solve this. So it's a complicated problem, and there's a reason why this has taken years and years and years, and the heavy tail distribution is a big part of that. What's the takeaway? Safety depends on engineering to mitigate rare high-consequence events. A takeaway that's just as important is that heavy tail distribution of surprises is a challenge to scalable deployment.